My name is Germán León. I'm coming from the University of Oviedo in the north of Spain on behalf of a team composed by researchers of the Universidad de Vigo, the company EOSOL, the European Space Agency, and also from my university. We are going to talk about communication inside lunar lava caves. So first, I would like you to imagine to stay in a room in a settlement like more or less this size, this wide, this height but above us we have the moon, we have the surface of the moon, but we are protected against meteorites with a stable temperature. That could be found in a lava cave. So lava caves are well known, and you can find it on the Earth. Here are two examples: one in Hawaii, another one in Saudi Arabia. Here in the left part of the screen is the Corona Tube. It's a volcano in the Canary Island in Lanzarote. Maybe you can. It's one of the longest lava tube in Earth. The red lines are the tube, and there are some points, and white points are the entrance that typically is called, in English is skylights, but in the Canary Island they call it jameo. And this is one of these skylight in human scale. More or less you can see how many rocks you can find there, and why a six-leg robot could be a very good solution to go into this cave. Also, there are some evidence of these skylights, not only on the moon, like this in the Marius Hill. On the moon, I think there is around 200 potential skylights, but also on Mars. Inside the cave, we don't know what you can find here. I collect some photos of our experiments, our measurement campaign in different parts of the La Corona tube. No, and sometimes some of the parts of the tubes are huge, and some other parts are small. Some parts have some terrace because it was produced by different lava flows. But also, here is another cave in Lanzarote that is younger. It has only 200, 300 years, and there is not this kind of terrace. But and it's more soft. So we don't know what we will find in the lava tube, but we have to prepare our robots to whatever they can find. So here is our proposal to explore or to give communication to a robot fleet that explore an unknown lava cave. So this is the scheme of a lava skylight, an antenna or a system, a base station should be on the top part of the cave or in the entrance. A first link will be established between this rover on the surface and the explorers that go in the first part of the lava of the skylight. A second communication link could be established between the robots that are on this skylight, but also a third one can be established with the robots that are inside the cave. More or less, we have done some measurements. The first one here is in this skylight in Jameo de la Gente that has a size very similar to the one on the moon. We put an antenna on the top part, and we measure in different points the amplitude of the signal between this transmitter that is on the top part and different points until the end in the point 7 that is inside the cave. We measure, or the receiver has two different antennas to compare two different systems. This pagoda is a circular polarized monopole antenna, and this quasi-jag is another vertical polarization antenna, but or a system with two different antennas to create a MIMO system. This line, the minus 70, minus 71, the signals that are above or show us that we can establish a medium data rate communication links around 150 megabits per second. Below minus 98 megabits per second, we will not have communication like in a Wi-Fi or like a Wi-Fi network. And between minus 71 and minus 98, we can have communication, but with different data rates. So you can see that until the point between 0.1 and 0.5, we can have good communication. Until the entrance of the cave, we can have communication. So we need to put a robot on the entrance of the cave to act as a relay. So this could be a top view of the exploring strategy, not to have a robot that acts as a relay. What we have done, so as we know, we don't know how is the cave. We don't know where to put where the robots have to be placed. We have developed a model, a propagation model for caves, or in two models, and we have test them in Lanzarote. So the first one is the idea is that the cave could be very, very huge, around 200 meters of wide. So we have some measurements in open space, in open air. What we have found is that if we put the receptor or at the same side, at the same point, or at the same height as the transmitter, the losses, the propagation losses, are worse than in free space. However, if we put the receiver in a position, in a high position around 3 meters, we have a positive interference of the terrain, of the echo, and we can have a better connection than in a free space. So we could use this in the exploring, this idea in the exploring process. Also, we have studied some or what happens when we have obstructions. So when you have obstructions or obstacles, you don't have a line of sight, so your losses increase highly, around 10 dBs, 15 dBs. It depends on the obstacle. Also, inside caves, we have also developed these models, and we have or measure also in different caves in Naturalistas also and in Corona, taking into account the echoes of the walls, of the ceiling, the effects of slopes and bends. The most or one of the biggest problem that the fleet can find is what happens in a bend. So when they don't have line of sight, we have found that an increment of losses will occur when you don't have, or when you are in this situation. Also, we measured a slope in another part of Naturalista's cave, and we found that a similar results of when we were in open space, that if the receiver is if one of the receivers is in a more height position, we can find an increment of the communication link. Also, so we have a lot of conclusions of this measurements campaign. So we can, the smooth of the roughness of the terrain is not important. If there is an obstacles, we can have diffractions, but it's an increment of propagation losses. If we have slopes, there are some parts that are in shadows, but there are other parts, or there are other positions that can be that propagation losses decrease. And in caves, also what we have seen is that the ceiling and the walls echoes increment the communication, so increment or decrease the propagation losses. So we can increment the distance when we can find or we can establish a communication link when we have line of sight, but if we don't have this line of sight, we maybe need to have another robot that act as a relay. So thank you very much. I want to appreciate the effort of the ESA that has supported this project. Thanks.
Thank you. It's great talk. Hang on. So we have plenty of time. Anyone have any questions? Let me start again then. Well, back about 10 years ago, initially I didn't think the lunar lava is a really good place for habitation, but now my thinking is slightly changed because technologies are getting developed. So it's really interesting. What's the next then?
Yes, I think for the next step is to translate what we have found in these propagation models to a robotic fleet that can act autonomy inside the cave when they explore.
Right, thank you. So any other questions, please? Here. And there as well. We have 2 questions.
Hi, so I was wondering, in general, what you showed seems to indicate that communication in this manner in a cave becomes very difficult as soon as there are a few bands. So what about a completely different thing, like just dragging along a thin cable and have cabled communication or something alternative? I guess.
Yeah, bueno, okay. So the problem of a cable is that you have to bring this cable to the cave. And this is an increment of mass, an increment of complexity. So it's okay. We, in a first analysis, we discarded this idea because it was a high increment of mass. But I have another solution could be to have small Wi-Fi hotspots and to throw it along the but the problem is that that possible problem is that data strategy decrease your data rate because you will have a lot of hopes, and that decrease your the data rate.
And next question, there was another question there. Can you bring the microphone, please?
I got a question on the electrical properties of the rocks that you had here in your experiment in comparison to those that you would encounter on the moon, because the moon is basically an environment where regolith is extremely dry. The electric constant is maybe similar to what we have on Earth, but conductivity is in comparison very low. How would your results change if you factor in the properties of regolith?
Yeah, two things. First, so maybe inside the cave there is no regolith. We don't know. So, and the second is that we have we have run a lot of simulation with different permittivity, with different conductivity, and the conclusion were more or less the same.